Well, I was gonna say more like so that everybody can get a little bit more of a break and have, especially from the professor side, just give us a little bit more time to prep, make sure that everything's working for everybody. But you know, here's what it is, and we'll get through. I mean, next semester I've got you guys for 410, which should be a pretty fun class. Much different than this class. That's what you're saying last class. Um, no, it's a you guys have a 7 a.m. That's a big day. 7 and then a 9:45. And we have a 12:30. Yeah, that's a rough day. But then you guys get 2 days where you basically have nothing, right? So, I mean, I used to do that undergrad, is I try to stack, or at least in grad school, I try to stack all my classes on like two days a week to not have anything. ASU is nice because you can schedule your classes so that you don't have anything on Fridays, which was always nice. Yeah, it's always there was always one day that's gonna be rough, but at least you know that one day is gonna be no classes for anybody, and then you guys have like a hard Tuesday and Thursday, then at least you're working Friday as well. That's not bad at all. What's up? What's up, Zach? You guys getting on with your vault designs? You guys have any issues with your vault designs? Make sure you send them, right? Because I'm super swamped on all the grading. All right. Well, I guess it's 12:30, so I guess we'll start. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us. I pray that you would just help us get through the next few weeks, help us get through the final part of the semester, get some rest and recharge and get ready for next semester. And we pray. Amen. All right, so including today, right, we've got 2 more total lectures, and then you've got a quiz next week on Friday, right? What's on the quiz? Great question. What is on the quiz? It's going to be impulse momentum, work energy, and gyroscopic motion. Those are the 3 things. Remember, I told you guys it would be pretty well set if you knew how to do that one problem from last class, right? The baseball bat one. So go back, watch, lecture episode 24 on YouTube. Make sure you understand how to do that problem. So, did we have anything? Work energy. So, not understanding work energy. The principle of work energy tells us that we change that there now we're good. All right, now we're good. Magic. Did the unplug replug. Okay, so as I was saying, work energy, right? Which was on here, right here. There it is. Work energy, right? Um, the kinetic energy at the start plus the amount of work that it takes to go from state 1 to state 2 is equal to the kinetic energy at the end, right? What is work? Work is just a force times the distance that we travel through. Now, in most cases, for the problems that we've been doing, we've been able to simplify this to conservation of energy, right? So work energy leads us directly into conservation of energy. If we don't have any conservative force, non-conservative forces like friction, we can assume conservation of energy. And in that case, conservation of energy tells us that the total kinetic energy and the total potential energy at the beginning, right, at some initial state, has to be equal to the amount of kinetic energy and potential energy at a final state, right? And typically we'll use the principle of conservation of energy in order to find a velocity, right? Typically use it like in that baseball bat problem, right? We needed the velocity right before impact so that we could use impulse and momentum to figure out what the velocity after impact was, right? Was that somewhat helpful for work and energy? Is there any other specific question from last class when we did some of those problems with impulse, momentum, and work energy together? No? Oh, that's not what I wanted. I want to clear up. Okay. Homework 7 is due a week from yesterday. Right, exam 3 on the 11th, which is a week from today. And then vault building test, right? We want to try to do that the Monday after the exam, right? Please, 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 please make sure you get me designs ASAP, right? I need a .stl file. Email or private forum it to me. If you're gonna use private forum, please make sure you list your preferred email address because I will CC you on the email to the lab staff. You guys may or may not have noticed, I don't know if you've looked, but I've named all of your CLC teams. You're all different members of the Guardians of the Galaxy. I think there's Groot, Drax, and Star-Lord. I think those are the 3. No, it was Groot. I didn't want anybody to get big heads, so it was Groot, Rocket, and Drax. Those are the 3. So you're either Team Groot, Team Rocket, or Team Drax. Okay. So good stuff. Last year I named the CLC teams after early 90s, late 80s WWF tag teams, which was pretty fun. All right, anyway, neither here nor there. I'm just stalling. Do we have any questions? Anything about what's going on, what the plan is, right? So after next week, we're done with all of the classwork stuff, and we're just focusing on CLCs from then on out, right? In terms of class time. So I will still show up to class. You guys can still use that time to work on your projects together, right? Like I said, if you can't do a build and test on Monday and you have to do it later in the week, we can try to work something out, but you guys gotta look at your schedules and let me know so I can try to clear some time. Okay. I also have to figure out when the room with the wind tunnel is going to be available. All right. Okay. So we're going to hit the last topic of the semester. We're going to spend a couple lectures on this. Topic 7, objectives. And topic 7 is gyroscopic and general 3D motion. So what we want to be able to do is identify the components of the gyroscope, describe the meaning of the rate of precession, nutation, and spin of a gyroscope, and analyze the dynamics of spatial machines and mechanisms. So this, we're turning it up to 11 here, right? Because general 3D motion, right? So everything that we have done so far has been discussing systems and analyzing them in 2D, right? In 2D. My microphone? That's the only thing I have connected. Oh, yeah, good. It wasn't my microphone. Sorry. Okay. Everything we've done so far has been 2D, so we're going to turn it up and we're going to look at how to do something in 3 dimensions, right? 3-dimensional analyses are needed to determine the forces, moments on the gimbals of a gyroscope, the points, the joints of a robotic welder, and the supports of radio telescopes, right? Everything that you build is 3-dimensional, right? And so what happens, right? We simplify these things for calculation purposes, right? To only be in 2 dimensions. And a lot of systems, that's fine. But what happens if you have something like this telescope, right? Where you need to calculate the reactions in 3D, right? Well, why would you need that? Well, the wind can blow from any direction, right? The way that your telescope sits on this is going to affect how those reactions and supports need to be designed, right? And we can talk about this in terms of impulse, momentum, and kinetic energy. So Newton's law in 3 dimensions isn't that different from what we normally do, right? So use the whiteboard for this. Say I have some mass here, right? And we'll draw it in 3D. There it is, the cube, right? Itself. Where I've got this x x, y, and z, right? So x over the y, and causes upward. Right, so I've got this cube, has some mass, it's in this coordinate system that's 3-dimensional, right? And if I were to apply a force here, right, we would just break it down into x, y, and z components, right? And so doing a Newton's law problem in 3D isn't that bad, right? It's just one more thing that we have to keep track of, right? And it's just one more moment that we have to keep track of. But everything has a component in the x, the y, and the z direction, right? So instead of writing it as an I and j vector, you write it as an ijk vector, okay? So how does impulse and momentum change? Right? The fundamental relationship developed for the plane motion of rigid bodies may also be applied to the general motion of 3-dimensional bodies, right? So the potato is back. Right? The potato is back. And check it out. I've got 4 separate forces here. And this is going to equal my kinetic diagram, right? So I've got my free body diagram is equal to my kinetic diagram. The sum of my forces is equal to mass times acceleration. The sum of my moments about the center of gravity is equal to the time derivative of my angular momentum about point G. Right, the relationship hg is equal to I omega, which is used to determine angular momentum for a rigid slab, is not valid for three-dimensional bodies and motions, right? So this is where it changes. The moment equation, you can't say anymore, this is equal to I alpha, right? You can't say I omega anymore in 3D. Why is that? Right. We'll talk about it. The current chapter is concerned with the evaluation of angular momentum and its rate of change. Right, so we're going to need to calculate angular momentum, and then we're going to have to take the derivative of the angular momentum to find out what the sum of our moments is. Okay, that's where we're going. So remember, angular momentum is given by this equation, right, where the angular momentum about the center of gravity g is just the sum of my linear momentum of r cross my linear momentum. Right. Right, the x component, right, so you can break this into x, y, and z components. You'll have some angular momentum about the x-axis, some angular momentum about the y-axis. Is disconnecting. There's literally nothing connected to this computer. It's triggering me. I'm sorry. We've made it this far. We made it 13 weeks, almost, the full 13 weeks without any technical issues. I don't understand what the problem is. I'm going to blame the CST 211 class that meets in here on the other days. It's Dr. K's fault. Dr. K, Dr. Staggs, and Dr. Wright. They're all going to get emails from me after class. Sorry. All right. Anyway. So if I want to find, I'm concentrating on the x component of my angular momentum. What is the x component? Is the angular momentum about the x-axis, right? And by looking at this, well, this is just the sum from I is equal to 1 to n, right, of y sub I times omega cross Ri minus z sub I times omega cross Ri, right, times delta m sub I, right? So essentially, remember what we're doing with angular momentum. We're summing the angular momentum of every single particle, right, inside of our rigid body. That's what the sum is. So when it comes down to it, your angular momentum about the x-axis, is actually a function of the angular velocity about the x-axis, the y-axis, and the z-axis. Okay? Now, this is a big complex equation, right? But it's necessary because remember, when we're talking about the sum of moments, this is the time derivative of this, right? So if I have this equation for x, y, and z, I should be able to take the derivative, right? So I can do some calculus to this, right? I can change my summations to integrals, right? So here we are. And I end up with these moment of inertia terms, right? So now this is no longer the mass moment or the moment of inertia about the center of gravity. This is I bar x, I bar xy, and I bar xz, which we can all grab from tables, right? That should have been something we covered in statics. And here are the y and the z equations. Okay? Here are the y and the z equations. So instead of having one nice angular momentum equation, we've got three component equations, right? I've got hx, hy, and hz. Hx, hy, and hz. Okay. We're doing okay so far. Do you have any questions? No, nothing yet. This is the derivation part, right? And right, what's the punchline? Well, these three equations are important, right? Here they are again. And that's great. Right, so the transformation of omega into hg is characterized by the inertia tensor for a body, right? We're not going to get super into tensors. The tensor is a 3x3 matrix, right? And here it is, right? You can see on the diagonal, you've got ix, iy, iz, and on the off axis, right, you've got these xy, xz, yx, zx, zy, and yz terms, right? With respect to the principal axes of inertia, we've got ix prime, iy prime, and iz prime. There's our tensor. And if we had something that lined up with our principal axes of inertia, we would get hx prime is equal to, and we can read those, I'm not going to go through those, right? But this is only valid if we are aligned with the principal axes of inertia, right? Which we haven't really talked about very much. Right. The angular momentum h sub g of a rigid body and the angular velocity have the same direction if and only if omega is directed along the principal axes of inertia. So this is less intuitive than when we did it in 2D, right? And I think we showed that when we do three-dimensional problems, right? We were talking about general motion. We did that one problem with the caster wheel, right? And we showed that applying a force in one direction doesn't always give us a straightforward or gut feeling response, right? And this is one of those times where we're going to have to trust our math. Right? We're going to have to trust our math and the fact that we did the calculations because it might not always jive with what we think intuitively is going to happen. The momenta, right? So the momentum, plural of momentum, right? Momenta of the particle of a rigid body can be reduced to L, right, which is the linear momentum, and linear momentum doesn't change. And the angular momentum about G, which is given by these three equations. What if you wanted to rotate, find the angular momentum about a point that wasn't G? Well, this is how we do it. H sub O is equal to R cross MV plus H sub G. It's the parallel axis thing, basically. Okay. So, we okay right now? Anybody have any questions? No, nothing? Okay. So you just essentially just complicated it, right? What's that, Zach? I'm sorry, I couldn't hear you.
This is the R bar.
Yeah, this is a vector. The book uses the bar instead of an arrow for some reason. to make it clear, that's a vector, and that's a vector. Well, all right, so it is a vector, right? But the reason that there's a bar over it, let me rephrase this. It is a vector, but the reason they're using a bar is because it's the vector that describes where the center of gravity of our body is, right? Any other questions? Angular momentum of a body that is constrained to rotate about a fixed point may be calculated from this equation, right? This was on the previous page. H sub O is equal to R cross M V bar plus H sub G. Essentially, what this is doing is this is saying, you know, what if I wanted to move this about point? What if I wanted to measure this from about point O, right? Again, the door. We care about the rotation about the hinge, not the rotation about the center of gravity. Or the angular momentum can be computed directly from the moments and products of inertia with respect to the frame OXY. Okay. Or we can do it this way, right? If you know all of the R's and all of the delta MVs, right? Then you can sum them all together and calculate them, right? Which just gives us this equation again, right? So if you know what Ix is, you know Ix, so right, if you know that tensor, right, you know Ix, Ixy, Ixz, Iyx, Iy, Iyz, and Izx, Izy, and I sub z, right? If you know all these, and you know all the different components of your angular velocity, then you have what you need. Right? So the principle of impulse and momentum, right? So that was Newton's law, basically, right? How does Newton's law change? For the forces, it doesn't change. But we need to use momentum to figure out the sum of the moments now, right? Because sum of the moments is equal to H dot G. Okay? So the principle of impulse momentum can still be applied directly to three-dimensional motion for a rigid body, right? So here's my momentum impulse diagram, right? I've got all of my momentum at the beginning plus all of my impulses is equal to all of my momentum at some final time. The free body diagram equation is used to develop component and momentum. The component and moment equations, or not momentum. For bodies rotating about a fixed point, eliminate the impulse reactions at O by writing the equation for moments of momenta and impulses about O. Right, so that's remember Dr. D's rule for how do we know where we want to sum our moments and sum our angular momentum? Well, you always pick the place that has the most forces, and in this case, you should always do it for the reactions because then you can not have to worry about solving for reactions. So concept question, right? At the instant shown, the disk here rotates with an angular velocity, omega 2, with respect to the arm A, B, C, which rotates around the y-axis as shown. Right, so this thing, this arm, is rotating in the, right, this is going to rotate around this whole thing. Let me draw it. This whole thing is going to move in this way around the y-axis, right? But as it's rotating, the wheel itself is also rotating that way, right? We want to determine the directions of the angular momentum of the disk about point A. So we need to choose all that correctly apply, right? So let's go back for a second. We're trying to figure out which one of these are positive and which ones are negative, right? So is X positive or negative? Is Y positive or negative? And is Z positive? Let's go back. You know what? Let me put this back up here. I'll write it on the whiteboard. Hx is equal to Ix omega x minus Ixy omega y minus Ixz omega z. Hy is equal to Iy x omega x is negative, right? Excuse me, negative plus I y omega y minus I y z omega z, and h sub z, sorry, marker is not great, is negative Izx omega x minus I z y omega y plus I z omega. Okay. So I don't know if you can read that or not. Hopefully you can. If you're watching this later, you can't. But at least you're looking at it right here on the screen. So here's the concept quiz based off of these equations, right? Let's start with the x direction. Are we assuming, do we think that we'll have positive x direction or negative x direction angular momentum, right? Do we think that this h sub x term, right? Remember the h sub x equation is Ix omega x minus Ix y omega y minus Xz omega z. Based off of this, do we think that we're going to have positive x or negative x? And is this equation going to come out positive or negative? What do you think? Who thinks it's positive?
Moving down, or
So, I guess,
well, I'm sorry. Oh, I see the y direction. Sorry.
Yeah.
I see
all right. So, show of hands, who thinks that x is positive? And who thinks it's negative? All right. We've got, it was 2 to 1 on that one. All right. We'll keep track. We'll talk about, let's look at the next one. We'll do them all at once. Hy, right? Hy is negative I yx omega x plus I y omega y minus I y z omega z. And I'll just put HC here too, so we can. All right, so Z1. Okay. So for the y-axis, what do we think? Based off of this equation in the top here. Do we think this is going to be negative or is this going to be positive? Who thinks it's positive in the y? Who thinks it's negative in the y? Who has no idea? Thank you for being honest. Appreciate it.
My best guess is that, I think I'll find out.
So it was negative in the x. I think that one is probably the most intuitive, right? So why, right? If we look here, this is 0, right? Omega x is 0. We got negative and negative. So this is probably going to come out negative, right? Why is it going to come out negative? Because omega y and omega z are both positive here, right? So the negative sign doesn't change. How do I know those are both positive? Well, it's the right-hand rule. Remember, x into y, positive z means I've got to curl x into y. Positive z is curling counterclockwise, which is the same way that omega 2 is moving. And then we're asked for it at this instant, right? If we weren't at this instant, remember, this omega 2 doesn't always line up perfectly as omega z, right? It could be some combination, but in this case, what we're looking at is fine, right? And z into x, right? So z into x, so this y direction rotation is also positive, right? It's positive in the y, right? Well, how do we know that? Well, all right. So remember, these omega x terms go away, right? And what we're left with is positive iy omega y minus iyz omega z. How do you know that that's going to be positive, Dr. V? Doesn't that depend on what the actual value of iy and iyz are? Well, here's the thing. Because iy is the principal moment of inertia, we know that it is going to be larger than iyz, okay? Which would make the term going to be positive, right?
So is X always negative?
Not in that, what do you mean always? So,
Negative because that way.
in this case, in this position, it is, right, in this moment in time. But if we rotated this slightly, this omega 2 wouldn't be perfectly about the z-axis anymore, right? So at another point in time, this wheel is now here, right? And this rotation is halfway through the xz plane, right? So it's actually partially rotating about here and partially rotating about z. It's just so happened that at the moment that we were asked to do this, right, this was perfectly aligned in such a way that gave us only omega z. So it's not always, but for this problem, because we don't have an omega x, that's why x is negative, right? So it depends on the configuration. It depends on the components of your angular velocity.
What point? I assume it's trying to figure out also like how you have the angular momentum in that direction.
In which direction? The x direction? So, so remember, we're talking about angular momentum. We're talking about things rotating about here. So as this moves and tilts, it's hard to describe, right? So if this was just like this, right, this would rotate like this, and you wouldn't have any twisting, right? But now, because I put this arm on it, right? Now, as this moves, this is going to want to turn, right? And it's trying to go this way because of the rotation. But as this moves, this arm is kind of twisting due to just existing, right? It's creating, because of the mass at the top here, as this rotates, it's going to cause some rotation in the negative x direction in this case, at this point. It's going to cause some momentum in that direction. That kind of. So think about it this way, if you, not in terms of momentum, but in terms of there's some moment that's going to be created because you have some offset weight up here, right? This is just going to want to, it's going to want to twist it. It's also positive in the z. Why is it positive in the z? The same reason, right? I sub z is going to be larger than I z sub y, or I z y. Why? Because I z is the principal moment of inertia, whereas the other one is the non-principal moment of inertia. Principal moments of inertia will be larger than their off-axis components. This stuff is not necessarily, again, right? I'm going to say it again. This stuff is not necessarily intuitive in 3 dimensions. It's not. Especially if you're just starting out and this is the first time you've ever seen it, right? As you do more of them, you get a better sense of how things move, but it's not necessarily intuitive. Do you have any other questions? We're doing all right? Maybe, maybe not. Let's try another one. A homogeneous disk of mass m and radius r is mounted on the vertical shaft AB as shown. We want to determine the directions of the angular momentum of the disk about the mass center G. Okay. In case you can't see it, I'll highlight this a little bit. Y, Z, X. Okay. Right, this has to be omega Y, right? Because it's only rotating in one direction. Okay. So we need to determine the directions of the angular momentum. All right. So is the x direction going to be positive or is it going to be negative? What do you guys think? Based off of this equation, positive or negative? That's the equation. Given what we have on this diagram, and we're going about the center of gravity, is this going to be positive or negative? Who thinks it's going to be positively directed in the x? Who thinks it's going to be negatively directed in the x? All right.
Since the disk is tilted, is it kind of rotating in the X?
And that's the thing, right? That's the trick. All right, so because we're doing it about point G, right, we do have to take into account this angle that we have shifted. So this y, right, we think about it this way, right? This is omega y originally. We'll just call it omega, right? But we want the components of omega. We actually have a component along x prime, right? We'll call this y prime. Z prime is not going to change, right? This is a rotation about z. So x and y are the only ones changing. So we need this component and this component, right? So we've got y x prime and y, or omega y prime, omega x prime, omega y prime, which this is going to be omega x prime is equal to, not this one, but omega sine beta, and omega y prime is equal to omega cosine beta, right? So if we look at that, we got omega sine beta, and then once again, we're going to say that that I sub x term is what is driving this, right? So we don't have a z. This goes away. That omega x is what's driving it, all right? So let's try it again for h sub y, now that we know that. Now that we got the trick out. So is it positive or negative in the y direction? What do we think? Remember, we've got nothing there. We can rewrite this, right? We can say I yx times omega sine beta plus I y. If I could write today, that'd be tremendous. Omega cosine beta. Okay, so is it going to be positive or negative here? What do we think? Who thinks positive? And who thinks negative? Oh, apparently I didn't put it in there. No, that's sweet. Oh, it's positive in the z. I think it's easy to see, well, maybe not easy to see why it's positive in the z. It's also positive in the z. All right, so what is it in the y? Let's talk about it. Is it at all? It turns out that it's going to cancel. There's going to be none in the y. There's another trick. Yeah, and then the z direction is positive. Looking at our equation, the I sub z term goes away. Right? This one's a little tricky. For the exact reason because I cannot tell whether or not this is actually rotating about z or not. Right? I don't know. This angle beta is not well defined for me. But right. Great. So now that everybody's more confused, let's talk about kinetic energy. Kinetic energy might surprise you to know that it works the exact same way that it did. In 2 dimensions, we're just adding the z direction, right? For translational kinetic energy, at the very least, right? So for translational kinetic energy, you've got x, y, and z velocity, and you just add the x, y, and z components together, right? And for energy, right? Well, energy is a scalar, so um, we're just adding all the total kinetic energy together, right? So you've got this x, y, z vector for velocity, and these terms again for rotational kinetic energy are going to change, right? So the axes correspond instantaneously with the principal axes here. Excuse me. T is equal to 1/2 m v bar squared plus 1/2 I x prime omega x prime squared, and so on. Right, so if we correspond with the principal axes, what are the principal axes? Principal axes are the major axes that we rotate about. Okay. With these results, the principles of work and energy and conservation of energy may be applied in a three-dimensional motion of a rigid body. Remember, energy is a scalar, so it doesn't matter what type it is, it doesn't matter what direction it's in. All that matters is the total amount of energy that we have, right? It's a scalar. It's a scalar. Kinetic energy of a rigid body with a fixed point. Okay. So if you have a fixed point, you're not going to translate, you're only going to rotate, and so you just have rotational kinetic energy, which this is our new equation for rotational kinetic energy, which also depends on Ix, Iy, Iz, and Ixy, Iyz, and Izx, right? Where do you get those from? So look up, use our tables, same places we get I for other things. If the axes O, X, Y, Z correspond instantaneously with the principal axes, then we don't worry about the second part of this equation with the Ixy, Iyz, and Izx, right? Because from when we wrote down the tensor a few slides ago, those would all be 0. All right, at the instant shown, right? So here's the thing. Here's our disk again, our first example. Which term will contribute to the kinetic energy of the disk? Choose all that are correct, right? So so here's the question, right? Are we in line with our, so Ix omega 1 squared, right? Omega 1 is completely about the y-axis, right? So Ix omega 1. Well, there's no, that's not going to come into play here, right? Ix omega 1. Omega 1 is omega y. That's not one of the available terms for us here, right? If we look at this equation, T is equal to 1/2 Ix omega x squared, not 1/2 Ix omega y squared, right? Even if you look at the off-axis terms, right? 2 times Ixy omega x omega y. Well, that term is just going to be 0 in this case, right? So anything that has an Ix in it can't be 1/2 Ix omega 1 squared. It would likely be this term, right? So what did we do, right? All we did was we looked at our energy equation, right? Here it is. Let me write it down. Right, T is 1/2. T equals 1/2 Ix omega x squared plus Iy omega y squared plus Iz omega z squared minus 2Ix y omega x omega y minus 2Iyz omega y omega z minus 2Izx omega z omega x, right? That's our equation, long equation for kinetic energy, right? Well, which one of these is going to apply? Well, if you look at this one, right, remember this is Ix omega y, right, because omega 1 is just omega y in this case. Well, this doesn't make sense and this doesn't make sense based off of the equation that we have, right? This one does, which is why it works. The other two also don't make any sense based off the equation that we have, right? Oh, sorry, there was this one too. IZ, I forgot about that one. Omega 2 is omega z, right? So this is 1/2 IZ omega z squared, which does make sense because it's right here. Right? So let me do it this way. Let's look at it this way. This and this go together, and this and this go together. The rest of these don't make sense with what we are given, right? Forgot about that one. What is that? I am 1/2 ml squared. Is this completely rotating?
That still blows my mind that it is different. So I'm here at the University of Sydney, my own stomping ground. I'm going to borrow some of their lecture gun equipment to hopefully teach you a bit about how gyroscopic precision works. The first thing I need to do is talk about vectors, because a lot of things in physics are vectors. That means they have directions. So an example would be momentum and force. These are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction, and if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we can make about rotating bodies, which is that torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You can call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now, before I go any further, let's have a look at this setup that I brought. I have a wheel here hanging from only one side by this rope. And so right now, there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. Well, what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum around that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be quite frictionful wheel. So check out Justin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get my head cut off by a bicycle wheel set.
Okay. Okay. So let's try a problem. Let's try a problem. We'll walk through this. So what's going on? All right, I've got a rectangular plate of mass M that is suspended from two wires. When it's hit at the corner D in the direction perpendicular to the plate. Immediately after impact, determine A, the velocity of the mass center G, and B, the angular velocity of the plate. Okay. So, well, it says impact in it. So we're immediately gonna just go with what? We're gonna say this has got to be a momentum impulse problem, right? It's got impact in there. So if it's a momentum impulse problem, we should have a momentum impulse diagram. So what do we have? I've got what? Well, I've got no initial momentum, right? I have 0 initial momentum, right? It starts from rest. We start it there. And this is a 3-dimensional object. So we've got this. Got some mass center here, G. And nothing's happened, right? There's nothing happens. The impact hasn't happened yet. We start from rest plus all of my impulses, right? Well, in this case, I have an impulse of F delta T that's applied at this corner D, right? So we'll call that D down here. This is corner A, B, and C. The entire plate has height B and length A. Right. Here's G. That means that this distance here has to be A over 2, and this distance should be B over 2, right? Because it's a rectangle, so we understand that the center of gravity should be halfway from each side. Not only do we have those, right, but we also have these supports here, right? So I'm going to have tension at point A, delta T, and tension at point B, delta T, right? Oh, no, I'd like to erase these, thank you. And we've got the weight of the plate, W delta T. We're doing this from the center of gravity. So we've got this coming out. This is going to be Z coming out towards us, Y pointed upward, and X pointed positive to the right. This will all be equal to my final momentum here. Right, my final momentum, which is L sub X in the I, L sub Y in the J, L sub Z in the K, and I've also got angular momentum here and here. This is going to be H sub X and H sub Y. Why don't we have any H sub Z? Because this force is directed along the Z axis, right? It's all in the Z, so we're not going to be rotating about the Z axis. Think of it this way. Here's my sign. I hit it with a force that goes this way. This is going to cause what, right? If I'm pinned at the top corners. It's going to cause a rotation this way, but it's also going to cause some rotation in this plane, right? But it's not going to rotate. Z is, it's not going to rotate this way, this way. Okay? It's not going to go that way. It's going to rotate like this and like this, right? This and this. So about the X and about the Y. Okay? And that's our setup. Right? We can talk about a couple of things here. Right, so we're going to assume that the wires remain taut, right? So that they're always in tension. What does that mean for us? Well, if we assume that these are taut, then the velocity of the center of gravity is only going to be Vx in the I direction plus Vy in the J direction. Sorry, not in the J direction. Vz in the K. Right, so if these stay taut, right, the lines stay taut, we're not going to move up and down, but we'll move in and out and left and right. Right, but we're not going to move up and down. And that means that omega is going to have an x component in the I and a y component in the j, right? So we talked about the rotation. We're not expecting any rotation around z. That's why. So if we have that, then we know, right, we can double check this and we can say that h sub g is therefore equal to I x omega x in the I plus Iy omega y in the j. We can run some numbers here. We can look up what I sub x is for a plate and I sub y is for a plate, and we'll plug those in. Right, that's what they are. Ix and Iy. So what's going on here? Right? Why are we doing this? Why do we want to set this up like this? What happened to z? Right. Well, first of all, we are saying that because of where g is in line with the principal moments of inertia. Right. It's in line with the principal moments of inertia. And g typically lines up with the principal moments of inertia. Where we have to include things that are not g is when we are talking about odd shapes of things and when we're not rotating about the center of gravity, right? But for this case, that center of gravity, g, lines up with the principal moments of inertia. So we don't have any ixy or iyz or ixz terms, right? All those are zero. So we're just left with this. All right. So let's look at trying to figure out the velocity of the center of mass. Okay. So let's start with the linear momentum. Okay, let's start with linear momentum. All right, and I shouldn't have this up here. That's not correct. There's no y, right? There's no y velocity. That's what this whole thing means right here. Dr. D messed up in his drawing. I apologize. Okay, the lines are taut. We're not moving in the y direction. All right, so what do we got here? If we look at this and we start in the x direction, right? X components of linear momentum. My initial linear momentum is 0. I have no impulses in the x direction. All I have is this. So it turns out that the center of gravity has 0 x velocity. What? That's nice. And I think that kind of makes a little bit of sense here, right? If the lines are going to stay taut, you wouldn't expect much swinging left and right. You would expect more forward and back, right? From pushing on the front of the sign. Right, so what about the z direction? Well, the z direction, we've got 0 plus, right? So the initial momentum in the z direction plus any impulses in the z. Well, I'm pushing on it, and that's actually a negative f delta t has to be equal to m in the z direction, right? M times v in the z direction. So v sub z is equal to negative 1 over m f delta t. and this is in the k direction, right? So we can rewrite our velocity vector here. So the velocity of the center of gravity is equal to 0 in the I minus 1 over m f delta t in the k direction. There it is. That's the velocity of my center of mass. How did we get it? Linear momentum. What was the tricky part? Setting it up. The tricky part about these is thinking through what we have and setting it up, right? Third dimensional dynamics is tricky, and they take a while sometimes. Okay. Any questions on how to find the velocity of the center of mass? No? We good? We good? We good. Okay. What about the angular velocity? We got to go after the angular velocity, right? Because this was the answer for part A. Angular velocity. Well, remember, looking at our, I want us to remember this, right? We wrote down this equation earlier. H sub g is equal to 1/12 mb squared omega x in the I plus 1/12 m a squared omega y in the j, right? So if we're looking at this, we are going to write x and y components for our angular momentum, right? So we're going to use angular momentum. Initially, we have 0, right? 0 angular momentum. Well, let's do this in the x direction. I've got 0 plus my impulses. Let's go back to our diagram. This force is being applied here. If we're measuring it from the center of gravity, it has a perpendicular distance of a over 2 away from g, right, as it's pushing. So it's creating a moment. Is it a positive or a negative moment? Well, it's negative, because if you look at the zx plane, z is coming out towards you, curl your fingers towards x. That means we're gonna have angular momentum in obviously the x direction, less obviously about the y-axis, and definitely not around z, right? Because remember, as this rotates, right, it's as this turns in this direction, right, in the x direction, it's going to want to, the wheel's going to want to move, right? It's going to want to shift out of plane a little bit, but it won't go about the z-axis. Okay. So really, we've got, I'm going to do this one in blue. Well, let me redraw this real quick. All right, so we've got omega 1 here. And I'm going to have some hg sub x, right? And some hg sub y. Because remember what we're doing too, right? We're really spinning about point O, but we want to know what the effect of moving everything to point G is going to be, right? That still takes into account everything that happens because point O is still in the system. We're just focusing just on the disk. But all the forces and all of the momentum and all of the energy still exists from the part that we're not analyzing. It's just we're shifting everything in. We're making this equivalent system that exists just of the disk, right? So we end up with H sub G. We write our H sub G equation as Ix omega x in the I plus Iy omega y in the J plus I z omega z in the K. Remember, omega z is still 0. Omega y still exists here, right? This is still going to have some y rotation. It's not, it's dependent on the thickness of our disk, right? But there's still some y rotation here. So we can rewrite these, right? We can say this becomes 1/2 m r squared omega I in the I direction plus 1/4 m r squared times negative r omega 1 over L in the J. Notice, how is this different than the angular momentum of going about point O? Well, when we went about point O, we had to take into account, right? When we went about point O, we had to take into account the length that we were away, right? The axle length. In this case, we don't include that anymore. We don't include that anymore. We can simplify this if we really want to, right? So H sub G is equal to 1/2 m r squared omega 1 times I minus r over 2L J. Right, so I can pull out some constants and do that, but you don't have to. What's that? No. We had chalk. We didn't have fancy boards. We had whiteboards, and we were lucky if you got more than one color marker in the classroom, to be quite honest. And we had PowerPoint. We didn't have to. I didn't have to do that. I'm not quite that old. I had to do that in grade school though. There was one person. Well, you know how you have classroom jobs in grade school. One person's job every month was to clap the erasers on Fridays. Everybody wanted that job because you got to go outside for like 15 minutes at the end of the day on Friday. I did. So in my high school, that's when I think everything was transitioning from chalkboards to whiteboards. And you used to get, so I went to Catholic high school, and certain teachers, we had Irish Christian brothers who taught there, and some of them would throw erasers at you if you weren't paying attention. Right? Some of them were. Yeah, good old days, right? 3-dimensional problems, there's just inherently more to it, right? We have to keep track of more things. Sometimes weird dynamics happen, right? Like when we watch the video, the Vsauce video, right? When you blow on the gyroscope, because it's rotating, you get different dynamics than you might intuitively want. But when you think about it for a second and what's happening, right, and the kinematics of it, right, things don't just stop moving when we apply a force. And I think that that's clear when we talk about things that are translating, but when things are rotating, it is a bit more difficult to get your mind around it, right? It's harder to conceptualize. So, I get it. Next class, the beginning of class, because this is all I got for today. We're gonna end a little bit early. Next class, we are going to finish up talking about precession, nutation, right? All those things that said in the topic that we wanted to know how to define those things, right? Come to class with any questions that you have, because it's probably not going to go the whole time. And if you start studying now, you'll be armed with questions to ask me for review for the exam, which is happening a week from today. We'll do it the same way that we did last time. You guys come to class, fill out your papers, hand them to me, and that'll be that. Okay.
What is the exam?
In there. So that's fantastic. I apologize if it's spotty. If it's bad, let me know, because if it's bad, let me know. Zoom also records it, but if my mic was cutting out, it's not going to make a difference.